Hey guys, I just get so frustrated with these passwords. They're always asking you to change your password, change your password. And the last time I did a password and it didn't accept it, it said I needed 8 characters. So it's very difficult to think of 8 characters for a password. So I picked Snow White and the Seven Dwarfs. I couldn't think of another 8 characters. I don't know. Passwords are so confusing. Anyway, sorry to vent there. We're going to be talking about enthalpy of combustion in this lesson. This is the second lesson in thermodynamics, so let's get rolling. When I give you values or you see values for these standard conditions, what you're going to notice is I will have, it looks like a degree sign. There'll be a circle up here. So what we've been talking about in the last lesson was delta H. So that's the change in enthalpy. And this circle here would mean at standard conditions. So I just want you to be comfortable with when you see this circle up here, what I'm talking about is under standard conditions. What does it mean to be under standard conditions? Well, it means that there is 1 atmosphere of pressure, which is the pressure at sea level. But even though we're higher than sea level, it's not that far different than 1 atmosphere. Liquids and solids are pure, so that means we're not dealing with mixtures when we're talking about standard conditions. If we're talking about solutions, we're talking about 1 molar concentration of solutions. So aqueous solutions will always be 1 molar. Unless stated otherwise, but that wouldn't be standard conditions, by the way. The energy of formation of an element is defined as 0, and we're going to talk about energy of formation later on. And then finally, the temperature is normally at room temperature. So room temperature is 25 degrees Celsius or 298 Kelvin. Questions might be somewhat easy, like, and under standard conditions, what would the pressure be? But I'm not going to be giving you values for enthalpy with different pressures. I'm not going to be adjusting it that way. So really the main thing I need you to understand is when you see this, what I'm talking about is standard conditions, because you're going to be seeing that pretty soon. Such as here. This table is available on the website. If you go to mrrast.com and look under thermodynamics and chemistry, you can download this. This is a table that you're going to be using on tests and quizzes that I give in thermodynamics. And these are enthalpy changes and under standard conditions for different combustions. Now, it's important to note that these are not everything that can combust. This is just a small sample of things that I'll use for my tests and quizzes, but it's certainly not extensive to everything that could be combusting. So anyways, we've got things like sucrose, which is table sugar. We've got octane, which is the main component in gasoline. Glucose, which is a simple sugar found in fruit. We've got propane, which we use in our labs with our Bunsen burners, and at least at our school. Ethanol is the drinking alcohol. This is the alcohol that we find in beverages and stuff like that. So that is ethanol. We have methane, which is a major component of natural gases. We have got methanol, wood alcohol, graphite, and hydrogen. So anyways, we have these values here. I've got the formulas written there, and I have the enthalpy change under standard conditions, and the unit for this is kilojoules per mole, so that if any 1 mole of these guys were to combust, this is how many kilojoules would be liberated. But let's talk about the formula for this. What are we talking about here? So when you look at something like this, so I'm going to talk about glucose right now. If we look at our table for glucose, we see that it's a negative 2,808. What does this mean? Enthalpy change of combustion. Anything that's combusting, and this is a very important concept that you should understand having taken chemistry, is anything that is undergoing combustion, in this case I'm talking about glucose, that would mean it's going to always react with oxygen. So combustion reactions will always be something that reacts with oxygen. And the products, if there's carbon in the reactant that's combusting with oxygen, it will always produce carbon dioxide. And if there's hydrogen, then it would produce water. So in this situation here, because there's carbon and hydrogen, it's producing carbon dioxide and water. If we look back at the table here, if we were to combust hydrogen, that would just be hydrogen plus oxygen. And since there's no carbon, hydrogen plus oxygen would only produce water. As well as graphite. When you burn graphite, because there's no hydrogen, that does not produce any water. So it would just produce carbon dioxide. Okay, so that's what this table means. All these things here that you see are reacting with oxygen. So there's actually a chemical reaction that's going on here, but in the table that we're looking at, you don't see the chemical reaction. You need to understand that the chemical reaction is a combustion reaction, so all these are reacting with oxygen. And then after you do that, you would balance the equation to see what the actual reaction is. But the point being, for every 1 mole that's combusting, this is how much energy is being released. So let's do a practice problem here. How much energy would be liberated from burning 15 grams of propane? Well, I always suggest the first thing you do when you get word problems is just take out what are the things you know in the problem and what are the things that you're solving for. So how much energy you're solving for that. So how much energy is liberated when you burn 15 grams of propane. Now to solve this, we're going to need to do a few things. We know from this table here, that we have a relationship between kilojoules and moles. However, this problem here is in grams, not moles. But at this point, you've been doing chemistry long enough that hopefully you understand that if you have grams, you can easily figure out moles. So we've got kind of a roadmap. The second thing is kind of formulate your plan. So since I have grams, I can convert that into moles using the molar mass on the periodic table. And once you have moles, you can convert moles into kilojoules using the standard enthalpy of combustion for propane. Now, get yourself a periodic table, maybe pause the video and try this out, see what you can do, and then come back. Hopefully, when you did this, you were trying to figure out the molar mass of propane, and you added up 3 carbons plus 8 hydrogens, and I got 44.097 grams per mole. That was the molar mass I got for propane. And then the standard enthalpy of combustion for propane comes from the table, and we looked that up on the table, and that's where we got this value here. So let's use some dimensional analysis to set this up. We can convert now our grams of propane into moles of propane. I set it up so that my grams will cancel with grams. I use the molar mass here, grams per mole, and now I've converted into moles of propane, and then I can convert out of moles of propane into kilojoules. So by doing this, I can cancel out the grams, which can cancel out the moles, and my answer will be in kilojoules. So if I take 15 and multiply, and then divide that by 44.097, and then multiply that by negative 2,219, my unit will be kilojoules. And I'll have negative 750 kilojoules would be my mathematical answer. However, you don't need to say negative in your answer because it says, hey, it says how much energy would be liberated. And so I would answer as 750 kilojoules of energy is liberated. Why? Let's think about this. This is the change of the system. The system lost negative 750 kilojoules. So if I was to talk about like going out to lunch and spending, I don't know, let's say we spend $10 at lunch. My account, I have less money now than I did originally in my account. So I have negative $10 in my account. But if someone was to ask me how much was lunch, I don't say negative $10. I would just say it was $10. It's implied in the question that I lost that money. So just pay attention to the way the questions are worded. The only time you would need to add a negative to make it more easy for you is if I were to say, what was the change in your, what was the change in enthalpy for this reaction? It's a negative change. Or for instance, when we talk about the lunch example, if someone were to say, what is the change in your total amount of money after having lunch? It was a negative $10 change. So the negative is often not part of the question. Just be careful. The question would have to say something about change in it for you need to use the negative question there. Okay, we've got some practice problems here. that they're different than the one we just modeled here. I'd like you to see if you understand what's going on. You're going to be using dimensional analysis and the things that you know to solve these questions. So pause the video now, because after you unpause it, I'm going to go through the answers in the way I solved it. So why don't you give it a pause, give a try for these 3 questions, and I will see you soon. Alright guys, so let's give number 1 a try. You've paused the video, you did it, so we're just gonna verify, and if there's any differences, then hopefully I can help make sense of where I went different than you did. So for the first thing in number 1, let's take a look at the things we know. We know that the mass, that we're solving for the mass of methane. So that's what we're looking for, the mass of methane. We know that the energy that was released in this reaction was 12,880 kilojoules. So that is what we learned from just the question. The second thing is, what's the game plan here? Well, I need to get I need to solve for grams, and I have energy, so I can say I can go from kilojoules. Since I have kilojoules, I can convert that into moles using our values on the table, kilojoules, the enthalpy of combustion, and then I can convert from moles into grams using the periodic table, using the molar mass on the periodic table. So to go from this stage here, on our table, we see that the enthalpy of combustion for methane was negative 891 kilojoules per mole. That's what it says on there, and that's our game plan. Now to get from moles to grams, we're going to add up the molar mass of methane, which on your periodic table you would take 1 carbon and 4 hydrogens, add those together, and so the molar mass of methane I got was 16,043 grams per mole. So if you add up a carbon and 4 hydrogens, you should come up with this number too. So make sure you do that. Don't cut corners, because when you do a test, all the practice you get will be useful. So that is second. That's the kind of things we have to solve this problem, because we came up with our kind of roadmap here. So the third thing is, let's do this. So we have kilojoules, so let's take what we started with. 12,880 kilojoules is what we started with. We can use this one here because we have kilojoules, so this would be the first conversion factor. We have negative 891 kilojoules per mole. That's the enthalpy of per mole of methane, because mole of what, everything has a different combustion enthalpy. And that was from the table. And now we can convert the moles of methane into grams of methane, and that's what we want to do. So we can say here that for every 1 mole of methane, there is 16.043 grams of methane. Kilojoules cancel with kilojoules, moles of methane cancel with moles of methane. We're going to be answering in grams of methane. So let's give that a try here. So I would take 12,880 divided by a negative 891. That negative work? Oh, there it goes. Now it's negative. Times 16, the molar mass, 0.043 equals. So we have got this number here, and to record this, I'm going to say it's negative 231.9 kilojoules, because I've got 1, 2, 3, 4 significant figures. Remember, trailing zeros don't count unless there's a decimal place, so I've got 1, 2, 3, 4 in my answer. So that's 4 significant figures. That's how much energy the change would be. But the question says, I'm sorry, kilojoules. The unit's grams. Sorry, guys. Okay, so so this is the grams, this would be the change in grams. In other words, it would lose this many grams of methane, but the question says what mass of methane must be burned. So I'm implying that it's being burned, that it is disappearing, so you don't need to answer it with a negative. Like I was talking to you guys before about the cost of lunch. Even though you might have lost $10, you don't say lunch was negative $10. That's the change in balance to you, but you would say 10. So we don't need to say this negative in there. So we would just say it's 231.9 grams of methane is needed to be burned to produce 12,888 or 12,880 kilojoules of energy. So this would be the appropriate answer that you would have to do, because the question didn't ask for the change. Let's take a look at number 2. Number 2. Okay, so number 2, what do we have in number 2? We have, in a lab, a student, what's given here, a student combusts 6.7 milliliters of hydrogen, so that would be volume. It says the lab's under standard conditions, and under standard conditions we have 22.4 liters per mole of gas for 1 mole. And the question is, what's the energy? What was the energy that was released in this? And we actually did this in our lab. We took, a lot of you guys produced some hydrogen when we reacted it with magnesium and acid, and we caught the hydrogen. A lot of us caught about 6-7 milliliters of it, and then we actually let it make a little quick boop in the graduated cylinder, if you guys recall that. So I'm actually kind of asking how much energy was released when we did that. It's very, very appropriate to what we did in lab. So let's take a look here. What do we got here? So I have milliliters of hydrogen, and I want to figure out energy of the hydrogen. So we're going to go milliliters to what? Well, I can't go right from milliliters to energy, but I can go, look at this, I can go liters to moles. So I got to get these milliliters into liters. So I'm going to go milliliters to liters, liters to moles, and then moles of combustion into energy using the enthalpy of combustion. So then we can go to kilojoules. Okay, so that's my game plan. That's what I got to do. I'm just going to use dimensional analysis and work right all the way through to that. Things I need to know. Well, I need to know that there is 1,000 milliliters per liter. I need to know the molar. No, I don't need the molar mass because we're not using grams here. So to do that, liters to moles, I have that right here. That there's 22.4 liters per mole. And then I need the enthalpy of combustion for hydrogen. And on the table, I see that it says that there is it releases 286 kilojoules per mole, and that's for when hydrogen combusts. That's the enthalpy, change in enthalpy of combustion for hydrogen. Okay, so this stuff here would be good enough to make it work. So let's plug it all together and solve. So start off with what we got. We're going to talk about the milliliters. I got 6.7 milliliters of hydrogen. And for every 1,000 milliliters of hydrogen, we will have 1 liter of hydrogen. That's the metric conversion. We got rid of the milliliters, and now we're in liters of hydrogen. At standard conditions, it says that there's 22.4 liters of hydrogen per 1 mole of hydrogen. So liters of hydrogen cancel out. Now we're in moles of hydrogen. And then using our enthalpy of combustion, we can see that for every 1 mole of hydrogen, it will release 286 kilojoules. Moles will cancel with moles. So that would be a good setup. We can see the units canceling out. We can see our answer is now going to be in kilojoules. All right, so let's plug in these values and see what we get. So we've got 6.7 divided by 1,000. Oh, not 10,000. 1,000. Which is divided by 22.4. Which is going to be multiplied by 286, and that's a negative 286. And I got this for my number, so my answer, and I'm going to record it with two significant figures. I got two significant figures here, so let's record that as negative. Remember, leading zeros don't count, so I haven't done a significant figure yet. So 8 and that 5, I'm going to take this 5 is going to round this 5 up. So only 2 would be 0.085, but since this number is 5 or greater, we're going to round that up. So 6. And my unit would be kilojoules. So there was a change, it lost this many kilojoules, which would say we don't need the negative, so we would just answer it as 0.086. So when we burn 6.7 milliliters of hydrogen, it released 0.086 kilojoules of energy. And it wasn't that big of a bang, was it? It was a little whoop, if you guys remember from class. So anyways, this would be the final step. Okay? All right. One more, guys. One more. We could do it. We could do it. Yeah. Let's do it. So the third question. Number 3. What's given to us in number 3? Number 3 says, how many calories? So energy, but the energy has to be in calories. How many calories? By the way, guys, if it's a capital C, that's what we use in America. When we ever have calories, it's a capital C. That really actually means, as far as units, a capital C is kind of a slang, in my opinion, term that we use in America for kilocalories. And if you live overseas or you travel overseas or another country, you might see it written as kcals. A kcal is, and it'll be a lowercase c. So capital C, this is actually a kilocalorie. But anyways, how many calories, in kind of a US way of saying calories, capital C, are obtained when the mass, when you have 75 grams of sugar, so that's sucrose, table sugar. So this is very appropriate. Some candy, a small little candy treat, not like a whole package, but maybe about half, a little bit more than half. 75 grams of a candy thing. How many calories are in it? That's a very appropriate question to ask. So I'm kind of curious myself. Let's take a look at this, guys. So 75 grams, like I said, is about half a pack of Nerds candy or something like that. How many calories are you going to get from that? So let's take a look at this. What do we need to do? Well, we've got grams. I need to convert grams to moles. And then I can convert moles, and I use the periodic table for that. Then I can convert moles into kilojoules from the enthalpy of combustion. And then I can convert kilojoules. I'm going to try to convert, remember in the question, I should maybe add an extra thing that was given here. Add one more thing. It says that for every 1 calorie, it's 4,184 joules. That was part of the question too. Forgot to write that. So that's really not just sucrose, that's anything. So I got to convert kilojoules into calories, but this is joules. So I need to convert the kilojoules into joules, and then let's convert those joules into calories. And so that's my game plan here. What's given, and that part here can go over here, that I have for every 1 calorie is equal to 4,184 joules. Kilojoules to joules, I know that for every 1 kilojoule, there's 1,000 joules. How about the molar mass? What's the molar mass of sucrose? Molar mass of sucrose, you would need to add up sucrose, which is going to be, sucrose is C12 H22O11. Let's just double check this real quick. Sucrose, did we write that right? C12H22O11. Yes, we did. Okay, so we got the right there. So we're going to take C times 12, H times 22, O times 11, and then we're going to add all these up, and that will give us C12H22O11. So 12 carbons. 12 carbons would be a molar mass of 12 times 12.011. That would be 144.132 grams per mole. Hydrogen is 1.008 times 22 of them. And if you got a scientific calculator, you can do this all in one string, but I'm just showing you the steps just in case you messed up on any of the steps. We can catch these steps here, or if I mess up, I can catch my mistakes. Oxygen is 15.999, and I've got 11 of them. 175.2 grams per mole. So let's add these all up. So I'm going to take that. Let's add that number to the 144.222, and we'll add another 22.176. So I've got the molar mass of this to be 342.297 grams per mole. That's the molar mass here. So so now we can go grams to moles with this, moles to kilojoules with that's one here, moles to kilojoules with the enthalpy of combustion for sucrose, and on our table I get that would be negative 5.644 kilojoules per mole. Okay, so grams to moles, I'm going to use this. Moles to kilojoules, I'm going to use this. Kilojoules to joules, I'm going to use this conversion. And then joules to calories, I'm going to use this conversion. So that's my game plan. It's all set. Everything looks reasonable. So let's give this a try. So let's give this a try. So I'm starting off with 75 grams, and I'm going to abbreviate sucrose because it is a very long formula, so I'm going to put SUC for sucrose. Suck. This problem sucks. The molar mass of sucrose right here, we say that there's 342.297 grams of sucrose per 1 mole of sucrose. We're in moles, so we got to here. Let's get to kilojoules. We'll use this number here. For every 1 mole of sucrose, it liberates 1 mole of sucrose combusted is 5,644 kilojoules of energy. So, and then we're going to go for every 1 kilojoule, there's 1,000 joules. And for every right here, for every 4,184 joules, there is 1 kilocalorie, or in America we call it just a calorie. So this is our setup for this one here. Grams of sucrose cancel with grams of sucrose, moles of sucrose cancels with moles of sucrose, kilojoules cancels with kilojoules, joules cancels with joules. Our answer will be in calories, and that's what we needed. We needed it to be in calories, so that's a good sign. We set it up right. Now let's see if we can do the math right. So we're going to take 75 divided by 342.297 times 5644, but that's going to be a negative number, times 1000, and that answer is going to be divided by 4,184. So I've got negative 295.57 calories. Now the question is, how many calories are in this? So that's assuming, again, how much it's there. How much is there? I don't have to say negative. I didn't ask what's the change in energy, so I don't have to put this there. And I've only got two significant figures, so I'm going to go to here, and that 5 will round the 9 up. So really, I could answer this as 300 calories, but I need to say that there's two significant figures here, and right now there's only one, and if I put a decimal place there's two. So to answer this properly, we need to answer it in scientific notation. So if I move the decimal place over 1, 2 times, I could say 3.0, now there's two significant figures, times 10 to the second calories. That would be the best way to answer this question. What's important here, what the basic thing is, so 75 grams of candy is 300 calories. I think it's kind of interesting. Sounds about right too. All right, guys, give this some practice, and hopefully it makes sense to you. Save those questions for me, and I look forward to seeing you again soon.